Hey guys, and welcome back to another A-level maths revision video. In this video today, we're going to take a look at some mechanics and we're going to take a look at moments. So this video is intended to be kind of a little bit easier. I'm going to do another video for some trickier moments questions, but hopefully this one shouldn't be too bad. Maybe just if you're looking for some last minute revision before any exams or any assessments, hopefully this will come in handy. So let's take a look at the questions here. We've got 3 questions here today, so let's jump straight into them. So this first question here, question 2. So these are all from the old M1 papers. So there's question 2 here, 2 parts for it. So what we've got here is a non-uniform rod. So, make sure you understand the difference between uniform and non-uniform. Uniform just means the center of mass will be directly in the middle of the rod. Non-uniform, it will be at a different place along the rod. So in this case, what we're told, so if I just show my pen back, I'm going to annotate on this diagram. So we've got a non-uniform rod AB, which has a length 3 meters and mass 4.5 kilograms. The rod rests in equilibrium in a horizontal position. We've got 2 smooth supports, P and Q. The main important bit here that we need are the 2 parts. The center of mass of the rod, that's at G. So that means the weight here, the mass, is at G. So if that's 4.5 kilograms, we'd write that as 4.5 G newtons. Okay, so that's for the center of mass. And then we've also got the magnitude of the reactions of the support. So the magnitude of the reaction of the support at P on the rod, so that's this point here, so that would be going up. And then we'll also have this one here at Q. And what we're told is that the magnitude of the reaction of the support at P is twice the magnitude of the reaction of the support at Q. So what that means is if I call this, say, R, this would in that case be 2R. Okay, so just calling that one R for reaction, that would be 2 lots of that. Okay, so that's the main bit we need for now. Let's see if we can start with this question. So part A, we want to find the magnitude of the reaction of the support at Q. Okay, so the first thing I'm going to do here is consider the fact that if I resolve the forces upwards should be equal to the forces downwards because it's in equilibrium. Okay, so what would that mean? That means 2R. So I'm resolving positive as being up. Okay, so 2R plus R, so it will be positive, minus 4.5G. So this is minus because it's down. Okay, at G, we're going down, so we're going opposite the motion that we need. So minus 4.5G. This is equilibrium, so it's equal to 0. Now what I'm going to do is I'm just going to solve here. Remember, we just want to find the value of R, so that's all we're going to do. We're just going to solve this here. So 2R plus R, so that will be 3R, minus 4.5G, so I'm going to take that onto the other side, because we want to solve this. So that's 4.5G, and therefore to get R, we just simply divide by 3. Okay, so 4.5G divided by 3, we just get 1.5G newtons there. You can give that in any equivalent form. If you'd rather write that as a decimal or number, whatever you prefer, that's absolutely fine. But I'm just going to leave it as it is there. Okay, so that's part A. Now let's clear this just to make room for part B. So let's just clear this manually. Right, let's have a look at this one. So in part B, we want to find the distance A to G. So we're looking at finding this full length here. So let's just write, or let's just annotate what we need. So we need this length here, which we already have. Okay, so we've got this bit here. That's 0.8. So the only thing that's remaining that we actually need then is this length here. If we can work out this length here, we just add it to 0.8, and we've got our length there. So how are we going to work out this distance? Well, we're just going to take moments, okay? I'm going to take moments at P here, so you can't really see it. I've kind of drawn over it, but this is P, so this is P here, okay? So that's P. So I'm going to take moments at P, and remember to assign a direction here, so whether it's clockwise or anti-clockwise. So I'm going to go clockwise here. So I'm going to take, oops, just change my pen color. So I'm going to take moments at P, and I'm going to take clockwise as being positive. Okay. It doesn't matter which way you take positive. It just usually makes your calculations a little bit easier, depending on which way you go. And that's something that will come with time and practice. So if I take this as positive, what I need to consider here now is the distance, basically, from G to P. Okay. So what's the reaction at G? That's 4.5 G newtons. So what I've got here, right underneath, is 4.5 G. And then we times that by the perpendicular distance. So from P to G, we don't know that. So I'm just going to write that as PG for now. Okay. Remember, that's what we need to solve. We need to solve for PG, and then we're just going to add it to the length AP. So we've got this part here. And this is going to be positive, and the reason for that is if you consider, so this is something important that we should kind of highlight here. So I change it to red. Imagine you was to act on this point here downwards, like it's the force is demonstrating. So we went down like that. So imagine I've got my finger here on like a ruler, and if I was to push down here on the ruler would go this way. Okay, it would go clockwise. So in that sense, it stays positive. Whereas if we consider taking moments now, or not taking moments, but considering this force here at Q, this force is going up, and if I was to push, again keeping my finger here, if I was to push upwards, the ruler would now go anti-clockwise. Okay, so in that case, it's going to be negative. It's opposing the motion that we've defined as positive. So again, all we're going to do here, so this will be a minus now in this case. So minus, bracket, 14.7, because this is the reaction here. That's the reaction here, that force. So that comes from your part A again, which is 1.5 G. That's 1.5 times 9.81. That's where that 14.7 comes from. So just so that's clear. So 14.7. And then we're going to times it by the perpendicular distance. So we're going from P to Q. So P to Q, remember we can actually just work out that length easily. The way we can do that, so again, this is why having a diagram is very helpful. We know this length here is 0.6. We know this length here is 0.8. So the remaining length then, if the full length is 3, then this length here from P to Q must be 3 minus 0.8 plus 0.6. So it's going to be 3 minus 1.4. So if we write that down, we times this by 3 minus 1.4. Okay. Now we're going to set this equal to 0. We have no other forces left, so we set this equal to 0. Now in this case, it's just a matter of solving. Remember, we want to solve for PG here. We want to find this distance. So this would be 44.1 PG. This part here will be minus 23.52. So at this point here, just plug all this into your calculator. Make sure you do it carefully. And this is equal to 0. And again, just solving for PG here, so I'm going to take this to the other side. 44.1 PG is equal to 23.52. So therefore, PG is just simply 23.52 divided by our 44.1 there. Okay, if you plug this into your calculator, it'll probably give you as a fraction. But I'm just going to write this as 0.53 recurring. Okay. So what we've just worked out there is the distance from P to G, which is 0.53333, so on. So in that case, the distance then of AG, the distance for AG will simply be the length of A to P, which is 0.8, plus the distance for P to G, which is 0.53, so on and so on. Oops, I didn't want to do that. That wasn't good. back. I made a mess of it. There we go. So, I'm having a bit of a nightmare. So let's give it another go. 0.8 plus 0.5333. Add these on your calculator, and what you should get here is 4/3. Okay? And remember, this is length. I'm working in meters, so this is 4/3 meters for the distance of A to G. Okay? So that's the first question done there. Hopefully not too bad. You know, these questions can be a little bit tricky, but hopefully with a clear diagram and, you know, with annotations, not too bad. So let's take a look at the next question then. So this is another question from another M1 paper. June 2015. We've got a beam, AB. The full length is 5 meters, and we have a mass of 25 kilograms. So let's just check. So it's a uniform rod, so the center of mass will be directly in the middle. So if this length is 5 meters, where's my pen gone here? There we go. So the full length is 5 meters. And again, let's just do our annotations here. So that would be approximately 2.5 meters here. It'll definitely be 2.5, but approximately on my diagram would say there. So it's 25 kilograms, that would be 25 G newtons. And we can also work out some other lengths here. So if we know this is a half, 0.5 meters, this full distance here is 2.5. So if this is a half, this must be 2 meters. Okay, so that's 2 meters. We can also apply the tensions here in the ropes. So this tension, I'm going to call it TA, because it's at the point A. And this one here, I'm going to call it TC, the tension at C. We've also got this point B here, which we know is a particle P, which is attached. So 60 kilograms. So again, we can write that in as 60 G newtons. Okay. So I don't think there's really anything else we can add just yet. And that should hopefully be everything. So let's have a go at tackling it. So we want to find the tension in the rope attached to the beam at A. So if we want to find the tension attached to the beam A, what I'm going to do here is I'm going to take moments, but I'm going to take moments at C. So I'm going to take moments at C, and that's going to give us the tension at A. So, again, let's define a sense of direction for positive. So, again, I'm going to take this as clockwise. So taking moments at C. Again, it doesn't matter though. You know, it'll just change the calculations slightly, but your final answer should be the same. So taking calculations clockwise as positive. So what would we get here? Well, first, let's consider the point A here. So I've got the tension in A. So if I've got my finger at C here, and I push upwards here, the tension at A, that's going to go clockwise. So that would be positive. So that's the tension at A. So that's okay. What else have we got? So we times this by the length. Well, if this part here is 0.5 and the remaining is 5 meters, then that'll just simply be 5 minus 0.5. So we times this by 4.5. Okay, remember, the force times the perpendicular distance. So tension A times 4.5 there. That's our distance. What else have we got? Well, let's consider B now. Again, it doesn't matter the order that you consider these in, but I'm just going to take it in a bit of a haphazard way. So if we consider B now, what would this be? Well, you push down at B, so this is a little bit easier with a different pen colour. Imagine I push down on this point B. If my finger's holding the ruler here, and I push down here, again, it's going to go clockwise. So this will also be positive. So this is going to be 60G, and we need to times this by the distance, okay? Which in this case, from B to C, would just be a half. Remember, we just need to keep going back to C at all points. So we went from A to C for the first part. And now here, we're going from B to C, so 60G, the force, times by the perpendicular distance. And finally, let's consider this point here, where our centre of mass lies. So our force is 25G. Now, if I've got my finger here at C, and I push down here at the centre of mass, the ruler's going to go counterclockwise or anti-clockwise. So in this case, this will be negative. So this is going to be minus 25g. And we need the perpendicular distance, which we worked out before, is 2 meters. So this is times by 2. Okay, and that takes us back to C. And it's in equilibrium, so this is equal to 0. Okay, so at this point now, this is just a matter of simplifying, rearranging in terms of T of A, the tension at A. So if we do that, this would be 4.5 TA. I've got 30g, 60g times a half, so that'd be 30g. And minus 25g times 2, so that would be minus 50g. And this is equal to 0. Okay, so if we take it up here just to finish solving this one, 30g minus 50g, so that would be minus 20g, and then we take that onto the other side. So what I've got here is 4.5 TA is equal to 20g, and then to get the tension at A, we're just going to do 20g divided by 4.5. Okay, and if you work that out, you should get 43.6 newtons. Okay, but you could give it in any appropriate form, but I think that's nicest for this one. So the tension at A, 43.6 newtons. And then the second part, we want to find the tension in the rope now attached to the beam at C. There's two ways you can do this. There's the easy way and there's the slightly longer way. So the slightly longer way is, again, to take moments. This time you could take moments A and just repeat what we did here, down here. But this is a longer way. There's a bit of a nicer way of doing this. So let's consider the nicer way of doing this. If we want the tension in the rope attached to the beam at C, remember, if this is in equilibrium, the sum of the forces going up minus the sum of the forces going down should be equal to 0. So in that case, T of A, which we just worked out, plus T of C minus our two forces down here, the sum of the two forces, so minus 25g plus 60g, this should be equal to 0. Okay, if we work this out, we can work out the tension at C. This is a quicker way of doing it rather than taking moments, but both methods are absolutely fine. The tension A we've worked out, that's 43.6. We don't know the tension at C just yet, and this part here, this would be 85g, but minus 85g. And this is equal to 0. So at this point here now, we're just looking to solve for the tension at C. So I isolate this now, tension at C here. That's going to be 85g minus 43.6. And if you just plug this into your calculator here, what you should get is 790 newtons there. Okay, so that's the tension at C. So like you can see, these questions become easier with time. And often there's some nicer ways of doing these questions. But keep practicing them. You will find them a lot easier. And like I said, I'm going to do a separate video on some harder ones. So let's take a look at the final question here in this video. I've accidentally wrote the wrong date. So this question is from 2011. Okay, so 2011. January 2011. So let's have a go at annotating the diagram first. So we have a uniform rod, or uniform beam I should say. So that means the centre of mass is at 3 meters here. So what's that mass? So that's 20 kilograms, that would be 20 g newtons. If this is 1 meter and from A to the centre of mass here is 3 meters, then this must be 2 meters. Okay, and then this remaining part here, this will be 3 meters. What else can we add on? Well, we've got our supports, we've got C, and we've got B. So we've got our reaction forces, our resultant forces I should say. So I'm going to define this as the reaction at C, and this is the reaction at B here. Okay, so let's have a go at tackling this one. We want to find the magnitudes of the reactions. Again, I'm just going to take moments here. Taking moments makes this nice and easy. So just check my pen colour. Taking moments So we want to work at the the magnitude of the reaction on the beam at B and at C. So truthfully, it doesn't really matter which one you take moments at here. I'm just going to take moments at C. And again, applying a sense of positive here for direction. Let's go anti-clockwise for this one. So anti-clockwise is positive. So we're taking moments at C. So let's consider our first force here. So let's consider B. So if your finger's at C and you push up here at B, then that will be going counterclockwise. So that's positive. So the distance then is 6 meters minus 1 meters. So that's going to be 5, and we times that by the force, which is RB. Okay, so 5 times RB. And then let's consider our other force here, 20 G newtons. So if my finger's at C and I push down here, apply this force, it's going to go clockwise. So this will be negative now. So minus 20 G, and then we just need to times this by the perpendicular distance to get back to C, which we can see is 2. Okay, it's in equilibrium, so this will be equal to 0. So at this stage now, we're just going to basically solve for RB here. So this is 5 RB. This would be minus 40 G is equal to 0. So 5 RB equals 40 G. So RB is equal to 40 divided by 5. So this is 8 G. Okay. But we also need to consider the reaction at C. So we've worked out that it's the reaction at B. That's 8G. We need the reaction at C now. So again, just like we did with the previous one, you can take moments now and do it at B. Take moments at B. But remember, just like we did with the previous one, there's a much quicker way of doing that. And that's to consider the fact that this is in equilibrium. So again, it sounds a bit babyish, but the sum of the forces going upwards minus the sum of the forces going downwards, that should be equal to 0. Okay. So if we do that then, so what we're saying is RC plus RB minus the force going downwards, so that's 20G. This should be equal to 0. In other words, the forces going up are equal to the forces going down. So we know RB is 8G. So what I've got here is RC plus 8G minus 20G is equal to 0. 8 minus 20 is minus 12. So I've got RC minus 12G is equal to 0. So in that case, RC is equal to 12G. And there we have it. So we've got our reaction, or the magnitude of the reaction at B, and we've got the magnitude of the reaction at C there. So 5 marks for that. And that's the question done. So I think the key with these moments questions is make sure you do annotate your diagram. They will very often give you the diagram, to start off with. Make sure you label the appropriate things. It will help massively, and then just take it step by step. Don't worry about where you're taking the moments. Generally, it doesn't matter. And it's good practice to try taking moments at different places. So give that, a try as well. But hopefully this video has helped. If there's any issues, if you notice any errors that I've made, like always, just leave a comment down below. Cheers.